in chapter 6 is just kind of some review, properties of exponents. It's probably been a little while since you've talked about this though, so I want to just take a day and kind of talk through this, look at some examples, and then I'll put the 6.1 assignment up there, which you can you get going on. Using properties of exponents. Let's review these. So the properties of exponents, if the A's and the B's, when we look at all these formulas up here, the A's and the B's are always going to be real numbers of any kind. Could be square roots, could be fractions, could be decimals, could be anything. But M and N, these are going to be the exponents. Those are going to have to be integers for now. Okay? So for example, let's take the first one, the product property. And you guys know the product property. A to the M times A to the N equals A to the M plus N. But the way we say that, remember, we always say something like this. If we multiply like bases, and real quick, what is, if I write something like A to the M, or if I used real numbers and variables, what if I wrote something like, let's say, x cubed? What do I mean when I say base? What's the base of this guy right here? Yeah, it's going to be A, isn't it? Right? The base is A, and what is it over here? X. Okay, and then of course when I say exponent, what am I talking about?
3 and M.
Yeah, so it's going to be M or 3. And if I take this whole thing together, I would call a power. Okay? So A to the M we would describe as being a power. Okay. All right, so the way we typically say this, remember, and this is, it's starting to get more important to be really exact with our language so we don't confuse ourselves. When we multiply like bases, right? So if I'm multiplying two powers that have like bases, what do? I add the exponents, right? So let's take a quick example of that. What if I had x cubed times x to the 7th? Yeah, I get x to the 10th. Exactly. Okay? No big deal. And you probably remember doing that stuff. Okay, next one. So that's what we call the product. And I don't care. I would never remember what those names are. It's not important at all. It's just important that you remember how to do them. Okay, power of a power property. Once again, the name is completely irrelevant. What we say instead is, if I take a power to a power, what do I do to the exponents? I multiply the exponents, exactly, right? I multiply, if I'm taking a power to a power, I multiply. If I'm multiplying like bases, I add. So for example, we just look at a real quick example of this. What if I had 3 squared to the 4th? That equals 3 to the 8th. Okay?
I have a question.
Yep.
So if we had like a big equation that had both of those in it, like which one would we do first?
Well, okay, we're going to do that. You're just going to follow a normal order of operations, and then as you run into these things using normal order of operations, you'll do them. Okay? Trust me, when you see it in the context of a problem, it'll make sense. And we'll do some today. Okay, power of a product property. So if I'm taking the product or the power of a product, so I've got two or more things that are being multiplied, and that whole quantity is being taken to a power, to an exponent. What do I do to the exponent? You distribute. You distribute over the product. Now there's a big distinction here though that you got to remember. Everybody listen to this very closely, because this is a common mistake and it's a big mistake. Okay, so I would do something like this, for example. If I had, say, 2x cubed, what would that equal if I simplify that? Okay, so I'm going to distribute. In this case, because the 2 and the x are being multiplied, that's going to look like 2 cubed times x cubed. And what is 2 cubed? 8. So I could actually, if I wanted to, even simplify that to 8x cubed in this case. Yes?
Can you say it's like a 2 and a 3, not an x?
Okay.
Would you 2 cubed times 3 cubed?
Okay, good.
So 8
Yeah, that's a good question. So Amanda's asking this, what if you had something like 2 times 3 cubed? What would you do there? Well, yeah, if I apply this product, that's the same thing as saying 2 cubed times 3 cubed. But Daniel, if I follow order of operations, what would I do here first? 2 times 3, right? If I followed order of operations, I would first multiply inside the parentheses because I can this time. 2 times x, I can't do anything with that, right? But in this case,
Should we do it the way we normally do it?
you'd do it, you'd follow normal order of operations, right? So that would be 6 cubed, okay? All right, so now what I want to show you here, though, I want to compare this last example. So everybody go back to this last example. When I had the product 2 times x, that quantity cubed, I distributed the power, but this is where people sometimes make a mistake. What if I had 2 plus x cubed? Do I distribute the power there?
Good, 2 plus x cubed.
What do you think, Caleb?
No, you would multiply.
Exactly. Okay, good. It's much more complicated than that. This is a big mistake. So everybody see this one. See this one. Look real closely. This is not equal to 2 cubed plus x cubed. Okay, what it actually equals is, it's pretty ugly. 2 plus x cubed equals 2 plus x times 2 plus x. Whoops, times, you get the idea. 2 plus x, yikes. So I'd have to FOIL that out. I'd have to FOIL this whole thing out, get an answer, and then distribute this one, right? And we'll talk more about that later in the chapter. We'll do problems like that. But that's a lot harder. I mean, that's, right, it's much, much easier to take the power of a product than the power of a sum. Doesn't seem like it should be, but it is. Okay, does that make sense? Everybody make sure you got that. Good?
Yep.
Okay, big important distinction there. Okay. Negative exponent property. Okay, this is a really simple one, but it's important too. Whenever I see, here's the way we've probably talked about this, this year and in the past. If I have a negative exponent, what does that negative exponent mean? Right, it becomes positive on the bottom, right? So for example, if I had something like this, say I had 2 times x to the negative 3. Well, that's equal to, the 2 stays on the top, but because I've got this negative sign in my exponent, that means it's going to be positive in the other part of the fraction. Okay? Make sense? So anytime you see a negative exponent, that's always equivalent to a positive exponent in the other part of the fraction. Now that can work. What if I see a negative exponent in the bottom? Because that could happen too. We're going to see some problems like that. Questions on this part over here real quick before I move
Yes, I don't understand this at all.
on. Okay, so
Negative fraction.
say it again.
Negative.
Because of this, because a to the negative m is equal to 1 over a to the positive m. By definition, that's what a negative exponent means. Okay? Now, the other thing this can do is if I have something like, say I had 2 divided by x to the negative 4. If I have a negative exponent on the bottom, what do you suppose that means?
Push it up to the top.
Positive on the top, right? It's always going to be positive in the other part of the fraction from where the negative is. Yeah.
Well, what if you're adding it? It's like 2 plus 4 to the negative 4.
Okay, now, hold that thought. Hold that thought for just a second. So this one's going to equal to the negative exponent on the bottom moves it up to the top as an x to the positive 4, right? Now what Caitlin's asking is, can I erase that? Everybody got that?
No.
Okay. What she's asking, and you tell me if I got this wrong, what you're asking, I believe, is what if I have something like 2 plus 3 to the negative 2, something like that? Like that? Okay, what I'd have to do is I would have to take this whole power and rewrite it as 1 over 3 squared. So what that's gonna become
2 plus that.
is 2 plus 1 over 3 squared, and I could simplify that to 1/9, couldn't I? So it's 2 plus 1/9. Okay? But because I've got that plus sign there, I've separated those two completely. Right? Okay. Zero exponent property. A weird one, but very simple. Any non-zero number to the 0 power, any of them, as long as it's not 0, is always equal to 1 by definition. So I could take the most bizarre thing you can think of, the most bizarre, it could be as big a number as you want too. I mean, I could take a Google. 10 to the 100th is a Google. To the 0 power is 1.
Why is that cool?
Like, yeah,
That's his definition of 10 to the 100 is Google.
Google?
Google. Yeah.
Why is Google called Google?
Google is called Google because of that, but they actually spell it wrong. The way you spell that is actually like that. So they changed the spelling a little bit. It's named after that number. But they didn't think that was very good spelling for some reason. Okay, and then the last big one is the quotient of powers property here. Now this one I do this in a way that is different, but you're gonna like a lot better than the way the book does it because it'll save you some steps in doing algebra with these. So let's take this guy. In fact, I'm gonna write this one on its own. I'm just gonna write. Don't worry, I'm just writing the same thing down again. So if I have a to the m divided by a to the n. So if I'm dividing like bases, I what the exponents? Subtract. Good. So that's equal to a to the m minus n. But it's also equal to 1 over a to the n minus m. Now, why would we do that? Here's why. Here's the rule you want to use instead. So listen very carefully. If you get this down, this will be very helpful to you. So say I'm doing something like 2 to the 7th divided by 2 cubed. 7, if I'm dividing like bases, right? And the exponent on top is bigger than the exponent on bottom. So what am I going to do here? That equals, I divided like bases, so
7 minus 3.
okay, good. So I'm going to get 2 to the 7 minus 3 equals 2 to the 4, right? Good. And then I can turn that into a number. Okay? Right? Okay, now what if, though, let's try something a little different. What if I have something like, say, x to the 9th over x squared? Okay, now if I follow the normal formula, I have to first write this as x to the 9 minus, oh, excuse me, I did that backwards. Start over. I gotta do this one again. I wrote the wrong, I wanted to do different exponents. So say I have x squared over x to the 9th. That's what I meant to do. If I follow the normal formula,
You give it negative.
yeah, look what I'm going to get. I'm going to get x to the 2 minus 9 equals x to the
7.
negative 7, which equals,
1 over x to the 7th.
aha, 1 over x to the 7th. Now here's a better rule. What you do instead, when I have something like x squared over x to the 9th, is I say, okay, I always look when I'm dividing like bases, and I ask myself, where is the biggest exponent? Is it on the top or the bottom? It's on the bottom. So then the base is always going to stay where it has the most power. So it's going to stay on the bottom, and I'll subtract from that exponent. So in this case, because 9 is bigger than 2, we put a 1 on top, right? Because the x is now on the bottom. I get x to the 9 minus 2 on the bottom, which is 1 over x to the 7th, in just one step instead of that extra step in there, right? So once again, when you're dividing like bases, you always just ask yourself, where does the base have the most power? And that's where it stays. And you subtract the other exponent from that one. Okay?
Easily done.
And then the power of quotients, this is no big deal. This is just like the power of a product. If I have a quotient all taken to a power, I just distribute. Okay? Just like I did with the product. So the quantity A divided by B to the M is just A to the M over B to the M. Okay? All right, so let's look at a couple quick examples. So try that one. Oh yeah, I can go back. And these are all in your book on the first page of 6.1. I tell you what I'll do. I'll even put those on a document and add it to the chapter 6 resources, and you can just print it out if you wanted to have it. Yeah. Yeah, go ahead. In fact, I could just copy that slide. How about I just do that? I'll just make a picture of that slide and put it on there so you can be under chapter 6 resources. Now you got it down. Okay, good enough. Okay, so what about this one then? So which property applies there?
Obviously,
Product property, yeah. I'm multiplying like bases, so what do? Add the exponents. So I've got the base, which is -5 to the 4 plus 5, so -5 to the 9th. And then if I actually do that, take the quantity -5. Remember, on a calculator, if you're taking a negative number to a power, you have to put it in parentheses. Okay? All right, make sense?
It's a big number.
Well, so this just means -5 times -5 times -5, 9 times. On my calculator, if I put that in, I have to make it look exactly like that, though. If I do this, well, in this case, you're accidentally going to get the same answer, but you won't for even powers. Okay, if I put this in my calculator and I forget the parentheses and it's an odd power, I'm still going to get the right answer because it needs to be negative. But if I do that for an even power, like if I had -5 to the 8th, for example, and I forget to put it in parentheses, I'm going to get a negative result when it should be positive. So whenever you're putting a number into a calculator, remember that if it's negative, you're putting it in parentheses. Okay? And a safer route is just to extend that thing I kept telling you in chapter 5. Remember in chapter 5, I probably said 100 times, do we ever square a negative? No, we always just square it's positive. Well, you can just extend that to all even powers, not just squaring. If I ever take an even power of a negative, all I have to do is just take the even power of the positive instead, because I know the answer has to be positive. Okay? What about this one? Okay, product, right? We got a product of like bases. If I multiply like bases, in this case the base is x, I just add the exponents. So x to the 7th.
What's that? Just kidding.
That's it. And for this reason, and this is kind of contrary to maybe your past experience, but at least in this chapter, you're going to be much, much happier, and probably from here on, you're going to be much, much happier to work with variables than numbers. Because I'm done. Variables are really easy to see when you have like bases. They're really easy to keep track of. And about this point in math, variables start to be a lot easier to mess with than numbers. What about this one?
Power.
Good. If I take a power to a power, I multiply the exponents. So 2 to the 12th. Okay? Which I could then simplify. What about this one? Yep. Go back. Well, okay. I mean, I can't. I'll put this up online too, so you guys can. This PowerPoint, in fact, it's already there. So you can go. You can click through this anytime you want to. I really don't think you probably need to write all this down.
Yeah, we do. You don't.
You can't, but you really don't. I mean, it'll be on there. I promise you. Okay. What about this one? Power to power. So I'm just going to multiply the exponents, 3 to the 8th. And 3 to the 8th, I could just throw in a calculator. It'll tell me that. What about this?
Negative exponent.
Okay.
Got it.
A couple things going on here. But before I do the negative exponent thing, don't I have like bases? right? So I've got -5 to the -6 plus 4, which is -5 to the -2. Aha, which becomes 1 over -5 squared. And then -5 squared is just 25.
What?
Okay? What about this? Much easier with variables, you'll see. What am I doing here? Good. I'm dividing like bases, and so I'm going to subtract. Now, which base, top or bottom, has more power?
Top.
Top, so we leave it on top. So it's x to the 5 minus 3, x squared, done. Much easier with exponents. Okay, what about this one? There's a lot going on here. Yeah, what are we going to do first on this one?
Multiply everything by 2.
Okay, good. I'm going to distribute the 2 because I've got a quotient to a power, and so I'm going to distribute that 2 to both parts. So I'm going to get r squared. Then on the bottom, I'm going to get s to the -5 squared. What do I have to do on the bottom?
Multiply 5 by 2.
Okay, power to a power, I multiply exponents. So I get r squared over s to the -10, but a negative power on the bottom, what's that mean?
Goes to top.
Positive on the top. That's it. Okay. Okay, now these are getting big, but it's no big deal. If we just follow these rules, even though that looks really ugly, this is not that big a deal. There's a couple things going on I can deal with. Now, what about, I'm going to have some stuff inside I've got to mess with, right? What about outside? What's this b to the 5th? What's the power of plain old b?
0.
1.
1.
No.
Good. Whenever I see a variable by itself or a number, it's always to the first power. Because remember, something to the 0 power, anything to the 0 power is just plain old 1.
Why?
Right. That's just that product, that weird property. It's kind of strange, but that's just the way it is. So, if I were to combine these guys right here, what would they combine to?
B to the 6.
Okay, all those become b to the 6th. Now, what's going on over here? If I have the quantity 7 times b to the -3 squared, what do I have to do there?
Multiply 32.
Okay, good. I've got two factors here. I've got the 7 being multiplied by the power b to the -3. I have to distribute that to both parts, right? It's good. So I'm going to get 7 squared times
B
to the,
-3 plus 2.
now what if I take a power to a power? -6, right?
And that just turns into.
And then look here, I've got b to the -6 times b to the 6. Those add up to,
1.
no, it's -6 plus 6. 0. So I end up getting 7 squared times b to the 0. And what's anything to the 0 is? 1. So that becomes 1, and we just get
8 squared.
49 for our answer. Right?
Wait, so what about the 1?
What's
8
49
times by 1 is the same number.
anything times
Oh, we're
1.
times in them. Alright. Shut up, guys.
Yeah, so there's a time sign there.
You guys will pull it.
All right, now let me click through that so we can just kind of see what they chose to do first, and it's fine, it doesn't matter. They chose to distribute the 2 first, right? So I get that. Now this is kind of slick. Look what they did here. They recognized, and this is a good way to accomplish it. If I see that this is a 1, and what if I multiply 3 like bases? Same property. I'm just going to add all 3 exponents at once then, right? So I get 49 times b to the -6 plus 5 plus 1. Which is 49 b to the 0, which is 49. Okay? Questions? Yes?
So, b to the 0 would just cancel out.
Anything except 0 to the 0 power is always equal to 1.
Okay, what is 0 to 0?
0 to the 0 is undefined. There's no answer to it.
Why?
It's what we call an indeterminate form in math. It could be anything. Okay? So that's something later in life when you take calculus, you'll start dealing with 0 to the 0.
We should
What
deal
if we
with
never
it
did
now.
calculus?
What? Oh, you should. Calculus is best.
Okay, how high is that?
This is right. It'd be not next year, but the following year.
So the other percent?
2 bucks.
Oh, we could never.
Senior year, we can do it.
You'll take pre-calculus, or college algebra, one or the other.
Which one's higher?
Be calculus.
I'm taking that one.
Okay, so moving on. Let's try some others. So what about this guy?
Yeah. Subtract top and bottom.
Now, this PowerPoint may do this the kind of the longer way. We'll do this our short way here. What do we do with this one instead? Yes, ma'am. Okay, good. Good. So we know if we've got a quotient, we're dividing like bases. So we always ask ourselves, which base has the most power, top or bottom? Bottom. Okay, so that means we move the base to the bottom. Understand I need a 1 on the top then, right? Okay. And then on the bottom I get x to the 10 minus 5. So my final answer is just 1 over x to the 5th.
Yeah.
Okay. Way easier with exponents.
Why can't we leave them as a negative? Like, why can't we
Well,
just put
okay,
them as a negative?
you can, but a lot of times we don't like to do that because it's confusing. And so typically what's going to happen in the textbook or in Moodle, like on the test, it'll say write your answer in terms of positive exponents.
What does it look like?
If I wrote it in terms of negative exponents, it would just look like, yep, you betcha. It would just look like x to the negative 5.
Yeah, but what if you wrote?
Okay. But usually the instructions almost always are on math problems in any textbook or in Moodle, it's going to be write your answer in terms of positive exponents. So we'd have to put the x to the 5th on the bottom. Okay? Okay, scientific notation. This kind of wraps it up for today. Scientific notation is very useful when you're dealing with very, very big or very, very small numbers. Normal size numbers, it's not important, but when the numbers start to get really far away from 0, very, very far away from the decimal point, I mean, these things are cumbersome to work with, right? So here's the rule we have for scientific notation. You guys, I know you've done this. If it's a very big number, if I have to move the decimal point to the left, then I'm going to be multiplying by a big power of 10. So all I have to do is just count the number of jumps from the beginning placeholder, the beginning decimal point, to where I end up when I get a number that is greater than or equal to 1 and less than 10, right? So when all is said and done, I need to have some number times 10 to some power. That number has to be greater than or equal to 1, so it can't be less than 1. It couldn't be something like 0.9. It has to be greater than or equal to 1 and less than 10. So it could be 9.99999, but it can't be 10. Because if it were 10, I would just scoot it over 1 more and get 1, right? So in this case, tell me when to stop. There's 1 jump, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Stop!
Stop.
Oh god.
Yeah, I know, I was scared. Okay, so there's my decimal, right? So I moved it 11 places, and so my final answer is going to be, that's where my decimal stays. So it's 1.314 times 10 to how many jumps? 11. Right? Okay, makes sense? Okay, now what if we had a number that was very, very small instead of being very big?
The same thing, but negative.
Move the decimal behind the first number, okay?
But then you have to put it.
Okay, real quick, I guess I got something else planned first, and then we'll do that. So how is this useful when we're dividing really big numbers? Here's how this is useful, especially when you want to estimate really big numbers. Because a lot of times in math and science, or even like engineering, we do what we call shirt sleeve calculations. I don't know where that came from. I guess somebody wrote on their sleeve sometime. But you want to just get an idea of roughly what's that answer going to be. And so if I were to write both of these two enormous numbers in scientific notation, I get something like 1.3 times 10 to the 11th on the top, and on the bottom I don't have to move it as far. I get 5.284 times 10 to the 6th. Now if I divide 1.3 by 1.314 by 5.284, that's where I could just make an estimate. I mean, they're going to give us an exact answer, but I could also just kind of make that an estimate. I could realize that that's roughly, You know, I could say that's about 0.25. Right, it's about something like 0.25. And to make it easier, if I wanted to, I could even make this, I could slide this decimal over 1 on the top. And I could even write that as something like, say, I could write it as something like 13.14, even though it's technically not a correct scientific notation expression, times 10 to the what? If I slid it back this way, 1, what does that do to my exponent?
10.
Makes it 10, good. Divided by 5 point bunch of stuff, 2 blah blah blah, times 10 to the 6th. And 13.14 divided by 5.2, we could say, okay, that's going to be, you know, we could probably come to the conclusion, oh, is that right? We could probably come to the conclusion that that's about, yeah, that's about right, about 2.5, right? 2.5 times 5 would be 12.5, but we're taking 2.5. Did everybody see this?
Yeah.
But 2.5 times something slightly bigger than 5 is going to push that up a little bit. So if we just wanted to get close, we could say that that quotient right there is roughly equal to 2.5, right? 2.5-ish. Times 10 to the what? Well, we'll just use our rules. 10 to the 10th over 10 to the 6th is what? 10 to the 4th. How about that? Times 10 to the 4th, and so that's going to become, if I scoot the decimal back over then, that becomes, if I move it, there's 1, 2, 3, 4, 25,000.
Sure.
Okay. Right? So if you didn't have a calculator and you wanted to do something like that, this is way too big of numbers to worry about. But if you write them in scientific notation, you can actually deal with them as smaller numbers and you know, make sense of
Are
it
you gonna
much
make
easier.
us have like a non-graphic calculator test for this?
No, because on the non-graphing calculator test, you can still do scientific notations.
Yeah.
I'm not really going to emphasize this particular thing on the chapter. This is, I want you to know how to do it, but it may or may not show up on the test. Okay, the last thing though, they didn't have an example in here. I want to show you just one of these. I'm sure you know how to do this, but how would I write this number in scientific notation? 0.0000000123. Okay, good. So how many places am I having to jump at this time? Now I'm jumping it to the right. It's a small number, right? It's less than 1. So I'm going 1, 2, 3, 4, 5, 6, 7, 8 jumps. So that's going to look like 1.23 times 10 to the what? Negative 8. See the difference? Because we moved the decimal to the right, it's that. Now that's going to make it a very, very small number, isn't it? Remember what it means to have a negative number up there. That's like saying 1.23 times 10 to the negative 8 is actually 1 over 10 to the 8. That's a very, very small fraction. That's 100 million. Okay? All right. That's a lot of stuff. We'll just call her quits for today. What's that?